Swayam Prabha. Digital India. Educated India.
In the previous lecture, we discussed about the Bronsted-Lowry classification of acids and bases. We talked about what is an acid and what is classified as a base, based upon the proton transfer or proton accepting abilities of a molecule. We also introduced pH. And now we will extend that discussion and discuss strong and weak acids and bases. So, what is a strong acid? A strong acid is a strong proton donor that is virtually completely ionized in solution. So, a strong acid will be a molecule which can easily donate proton to another molecule, and in the solution it is virtually completely ionized. So, this strong proton donating ability makes a molecule as a strong acid. For example, if we take HCl, HCl in water easily donates proton, HCl easily donates proton to water and forming hydronium ion plus chloride ion. And in such a reaction, we say that HCl is virtually completely ionized in solution in the form of hydronium ion and chloride ion. So, therefore, we call HCl as a strong acid. Similarly, if we consider sulfuric acid in water donates a proton to water very easily and forms H3O plus HSO4 minus. This is also we treat as virtually complete ionization, and that is why sulfuric acid is a strong acid. And there are certain parameters which will classify about a particular molecule being a strong acid. And that parameter we discussed in the previous lecture also is acidity constant. Let us take a look at this comment. The acidity constant of a strong acid is greater than 1. This is true for strong acids, that if the acidity constant is greater than 1, then pK is equal to minus logarithm of Ka. So, if Ka is greater than 1, then pKa will be less than 0, it will be negative. And that is what is commented over here, that acidity constant of a strong acid is greater than 1 and the pKa of a strong acid is negative. Okay. Now, what about a strong base? A strong base is a strong proton acceptor and it is virtually fully protonated in solution. When we discussed about strong acids, we said there is a virtually complete ionization in solution of the acid. And now when we are talking about a strong base is the one which is a strong proton acceptor, and it is virtually fully protonated in solution. Let us take one example. O2 minus in aqueous form plus H2O forms 2OH minus. This oxygen 2 negative itself will not exist in solution as such. It is virtually protonated. You see over here it immediately interacts with water and forms hydroxide ion. That is what is the meaning of that O2 minus is a strong base and it is a strong proton acceptor. It is accepting a proton from water and virtually it is fully protonated. Okay. Now, let us look at few more comments. The conjugate acid is a very weak proton donor. Now, if this is a base, its conjugate acid is going to be 2OH minus, this OH minus, and OH minus is an extremely weak proton donor. It will not give its proton to water. That is what is the meaning of this sentence. The conjugate acid is a very weak proton donor, and very weak proton donor means the acidity constant is going to be very, very small. And this conjugate acid OH minus is an extremely weak proton donor to H2O. So, these are some of the properties of the strong base and its conjugated acid. Now, let us talk about a weak acid. Weak acid is a Bronsted acid that is incompletely ionized in solution. There are several molecules which will not undergo complete ionization in an aqueous solution. And this ionization, let us also keep in mind whether something is fully ionized in a given solvent. It depends upon the type of the solvent. A certain molecule may not be ionized in a given solvent, but it may be fully ionized in a different solvent. But since here we are talking mostly about the aqueous solution, so let us restrict our discussion to the aqueous solution. A weak acid, when we talk about an acid in an aqueous solution, as seen in this slide, a weak acid is a Bronsted acid that is incompletely ionized in solution. That means the Ka is going to be less than 1, and since Ka is less than 1, now let us go back to this discussion. If Ka is less than 1, I substitute over here, then pKa will be greater than 0. Let us take certain examples. We take example of acetic acid. Acetic acid in water will have this ionization reaction. The proton is donated to water and hydronium ion is produced plus CH3COO minus ion is formed, and the pKa value is 4.7. Now, let us take another example. HSO4 donates proton to water and forms H3O plus sulfate ion, and the pKa value is 1.92. If you compare these two pK values, pKa value of acetic acid is higher than the pKa value of HSO4. that if pKa is high, Ka value is low, and if pKa value is low, Ka value is high. So, therefore, going back to this slide, the pKa value of the second reaction, that is HSO4 minus plus water forming H3O plus sulphate, pKa value is lower. That means HSO4 is a stronger weak acid compared to the weak acid CH3COOH. Why I am saying these weak acids? Because these are not completely ionized in solution, and the ionization, if it is not complete, then Ka is less than 1 and pKa values will be positive. So, thus the comparison of these pKa values suggest that HSO4 is going to be a stronger weaker acid compared to acetic acid. In fact, HSO4 is a conjugate base of H2SO4. H2SO4 itself is a strong acid and its conjugate base is HSO4 minus, and HSO4 minus is only a weak acid, because this itself can further participate in protonation of water and act as a very weak acid. Let us look at some of the comments. Since pKa of HSO4 minus is smaller than that of acetic acid, HSO4 minus is a stronger weak acid than acetic acid, and that is what I was saying, that the comparison of these pKa values suggests that HSO4 is a stronger weak acid than acetic acid. This means that HSO4 is more fully ionized in a solution at the same molar concentration. In other words, if you take equimolar solution of HSO4 minus and acetic acid, then the ionization will be more in HSO4 compared to that in acetic acid. So, this kind of information is available once we have the values of pKa. We can comment upon their acidity, or we can comment upon their proton donating abilities. Now, let us talk about weak base. What is a weak base? A weak base is a Bronsted base that is only partly protonated, not fully protonated, it is partly protonated. And again, the usual example will be ammonia plus water forming ammonium ion plus hydroxyl ions. And if NH3 is a base, its conjugate acid is NH4 plus. But this is an example, ammonia is an example of Bronsted base that is only partly protonated. In general, the conjugate acid of a weak base is a weak acid. For example, you see ammonia NH3 is a weak base and its conjugate acid, which is NH4 plus, is actually a weak acid. Actually, when you classify this acid and bases in Bronsted-Lowry concept or classification, whether we talk about an acid or we talk about a conjugate acid, or whether we talk about a base or conjugate base, an acid is an acid, a base is a base. Therefore, the classification applies to both the acid, whether it is a strong acid or it is a weak acid or it is a conjugated acid, strong base, weak base or conjugated base. Now, let us look at the next comment. NH4 plus ammonium ion is a weak conjugate acid of ammonia, and you see if the acid is very weak, that means the pKa value is going to be high. That is why pKa of ammonium ion is equal to 9.25. This is how the data on pKa values should be interpreted. Whether a given molecule in aqueous solution turns out to be a strong acid or a weak acid, a strong base or a weak base, it will lead to change in pH of the solution. And if the molecule ionizes completely in, let us say, aqueous solution, for example, if we talk about HCl and we said that HCl ionizes virtually completely in water, then the pH calculations become a little easy. However, in the case of a weak acid or a weak base, since the ionization is not complete, therefore, the calculation of pH values becomes a little difficult, a little tedious, because you will have to account for the incomplete dissociation of acetic acid in solution or incomplete ionization of the weak acid or an incomplete protonation of the weak base in solution. Let us take an example. Calculate the pH of 0.15 molar ammonium chloride, the activity coefficient of a univalent ion in a solution of 1:1 electrolyte of this concentration is about 0.6. In fact, I am revisiting this question. This question I have discussed earlier also, and here again I am discussing in context of pH. So, let us quickly go through the solution. Since we have ammonium chloride, the corresponding equilibria is ammonium ion plus water forming H3O plus ammonia. And Ka, acidity constant for this weak acid, will be activity of hydronium ion into activity of ammonia divided by activity of ammonium ion. And as we discussed earlier, since the solution is dilute, we can replace activity by molality. And also further noticing that the two molalities of H3O plus and NH3 are going to be same by the reaction stoichiometry. We are assuming that the molalities are same. And once again I will highlight here that we are approximating activities by molalities or by concentration. And therefore, once you equate these two, the molality of H3O plus can be calculated from this expression, that is Ka into m into ammonium ion m naught square root. I am not going into that much detail because this question I have already discussed. So, once we have the value of activity of hydronium ion or the molality of hydronium ion, we can easily calculate the pH. So, first the molality of hydronium ion is evaluated from the knowledge of Ka and the concentration or molality of ammonium ion, and then m of H3O plus comes out to be 9.2 into 10 to the power minus 6 mole Kg, and activity is equal to activity coefficient into molality by m naught is 1 mole per kg, activity coefficient is 0.6 and molality is given as or the calculated as 9.2 into 10 to the power minus 6, the overall activity comes out to 6 into 10 to the power minus 6 once you substitute this activity into the definition of pH, pH is minus logarithm of activity of hydronium ion concentration, and activity of hydronium ion concentration we just calculated, and by solving this you get an answer of 5.2. So, pH turns out to be 5.2. In this numerical problem, what we need to appreciate is that the activities can only be replaced by molality if we assume the solution to be very, very dilute. And if the solution is not dilute, we must account for activity coefficients. As it is done for ammonium chloride, we are using the activity coefficient value of about 0.6. So, what we have done is we have had a detailed discussion on what is an acid, how to classify a base, what is a strong acid, what is a strong base, what is pKa, and what information do we get from pKa. We also discussed about autoprotolysis constant of water and the temperature dependence of the autoprotolysis constant of water. Whether pH is temperature dependent or not, this also we discussed, and we found out that yes, pH is dependent upon temperature. We also discussed the method to calculate the pH of a solution. And since we are talking about the weak acids and weak bases, there is one more question on equilibrium that I would like to discuss over here, because these weak acids, or there are many molecules which tend to dimerize in solution or make higher order oligomers. We will here talk about the acetic acid. This question is actually based upon the concept of equilibrium constant. Let us read the question. Acetic acid was evaporated in a container of volume 21.45 centimeter cube at 437 Kelvin and at an external pressure of 764.3 torr, and the container was then sealed. The mass of the acid present in the sealed container was 0.0519 gram. The experiment was repeated with the same container, but at 471 Kelvin, and it was found that 0.0380 gram of acetic acid was present. Calculate the equilibrium constant for the dimerization of the acid in the vapor and the enthalpy of vaporization. It is about acetic acid dimerization. Let us consider a general process A in equilibrium with 2B. Right hand side is dissociation, left hand side is dimerization. And if n is the number of moles at equilibrium and alpha is the degree of the dissociation, you have 2n alpha. Total n, total number of moles is equal to, you add the both, it will come out to be n into 1 plus alpha. N into 1 minus alpha plus 2n alpha will come out to be n into 1 plus alpha. So, mole fraction of A will be equal to this divided by this 1 minus alpha over 1 plus alpha. Mole fraction of B is equal to 2 alpha over 1 plus alpha, this divided by this. Therefore, partial pressure of A is going to be 1 minus alpha over 1 plus alpha into total pressure, and partial pressure of B is equal to 2 alpha over 1 plus alpha into total pressure B. And when we write the equilibrium constant for A going to 2B, it is Pb by P naught raised to the power 2 over Pa by P naught. And you need to substitute. Let us substitute for Pb and Pa. Pb is this, it will be 4 alpha square over 1 plus alpha square into P by P naught square, that also will come, divided by Pa by P naught, it will be 1 minus alpha over 1 plus alpha into P by P naught. Once you rearrange or once you cancel out the common factors, we can go to the slide. For A going to 2B, as I just discussed, that after this discussion K will come out to be 4 alpha square into P by P naught over 1 minus alpha square. And once I know the value of alpha, then I can easily get equilibrium constant. If I treat the gases to be ideal, then I can use this equation, P V is equal to N RT. N is the total number of moles, and the total number of moles we have found to be 1 plus alpha RT. This point is to be noted. PV is equal to nRT, but the total number of moles that we have just found out is n into 1 plus alpha. So, therefore, one can get alpha from here. How do you get n here? N is equal to mass divided by molecular weight. And in each case, let us look at the slide, in each experiment the mass is given. In one case it is 0.0519 gram, in other case it is 0.0380 gram. So, therefore, PV is equal to nRT. In fact, this n should be read as n total, which is equal to 1 plus alpha into nRT. With n is equal to mass divided by molecular weight, we get alpha. You rearrange this, alpha will be equal to PV by nRT minus 1, and it comes out to be 0.392. So, once you know alpha, you can easily calculate K. What you are getting is K is equal to 0.740. This is at 437 Kelvin. Similar calculations for the second experiment at 471 Kelvin, K will be equal to 0.764. Now, you have K at two different temperature and I can easily calculate the value of enthalpy. This equation we have discussed many times. This comes from the integration of the Van 't Hoff equation between two limits of Ti and Tf, and after the substitution we get the enthalpy to be plus 103 kilojoules per mole, but remember that this enthalpy is for the process A going to 2B. Therefore, dimerization, which is the reverse reaction, the enthalpy of dimerization will be negative of this, will be minus 103 kilojoules per mole. So, we have discussed the various aspects of weak acids, weak bases, how to classify weak acids, how to classify weak bases, pKa and its relation to its ability of the molecule to donate or accept protons. And also how to deal with the values of pKa in terms of delta G naught, as we described in the previous lecture, that Ka is eventually connected with the standard reaction Gibbs energy, because Ka is an equilibrium constant. And whenever you have the values of equilibrium constant, its temperature dependence can give you other thermodynamic properties. So, I hope we appreciate that the thermodynamic properties and their temperature dependence gives a lot of information which can be used to discuss many processes both qualitatively and quantitatively. And we have taken several examples to demonstrate this. There is still more to be discussed about acid and bases in relation to the buffers, because when we talk about the biological systems, the choice of buffer becomes very important. Therefore, which salts to be chosen to prepare a buffer and what is a buffer, these matters we will discuss in details in the next lecture. Thank you very much.